Today we're going to look at directional derivatives. First, we will introduce the definition of a directional derivative, and then we'll see how the directional derivative allows us to give a good interpretation of the gradient vector. All this material can be found in section 2.6 of the textbook. Let's remind ourselves about the definition of a partial derivative. Consider a scalar valued function of two variables. Then the partial derivative of f with respect to x was defined via this limit. Geometrically, we think of this limit as computing the slope of a certain curve lying in a plane that has fixed y value and is parallel to the z-axis. Similarly, we had the definition of the partial derivative with respect to y. Here we fixed x, kept x constant, and intersected our graph with now another vertical plane parallel to the z-axis. Again, the partial derivative with respect to y determined the slope of the curve at a point on the graph. So an interesting question we may ask is, can we make sense of the rate of increase or decrease of f in other directions? What we mean is, can we use different planes to come up with different curves that arise as the intersection of this plane with the graph of f, and consider about the rate of increase or decrease of these curves at points? So the answer is yes, and this is precisely what the directional derivative measures. Let's take a scalar valued function of two variables and choose a point in the domain of f. Now let v be any vector. This doesn't have to be a vector in x, this is just any direction vector. We define the directional derivative of f at a in the direction of v to be the following limit, should this limit exist. Notice the similarity with the definition of partial derivatives that we've seen before. What the directional derivative computes is precisely what we're after. We take our direction vector v, this blue vector here, from our point AB. Now we take a vertical plane that lies along v and passes through the point AB, intersect that with the graph of f to give us this curve, and now the directional derivative computes the rate of change of f in this direction. This is exactly the same as computing the slope of the tangent line through this point on the graph. For example, using this limit definition, if we take this function, we can compute the directional derivative to be 44. The directional derivative is a generalization of the partial derivative. The partial derivative is computed actually as a special case of the directional derivative. In the case that f is differentiable at a, in fact, the partial derivatives can completely determine the directional derivative, as we'll now see. Given any scalar valued function of two variables, if that function is differentiable at a point, then the directional derivative exists for any direction, and moreover we can compute the directional derivative without having to go through our definition using the limit. The directional derivative can be computed as the product of the 1/2 gradient vector multiplied by our 2/1 column vector v. So for our example above, we would compute that the gradient of f at the point 1, 1 is the row vector 5, 18. And we can easily see in this instance that multiplying this row vector by the column vector that we had in the previous example gives the answer. The useful thing about the directional derivative is that it provides us with an interpretation of the gradient vector of f at a point A. Let's consider the following very special situation. Suppose that f is differentiable at A and u is a unit vector. This means that it has magnitude or length 1. In this instance, the directional derivative, as we've just seen, can be computed as the product of the gradient of f at A and the unit vector u. Well, if we now just assume that the gradient vector was in fact a column vector, then we'd see that this product of matrices is exactly the same as the dot product of the column vector defined by the gradient and u. We know how to compute dot products using the angle between two vectors. So here theta is the angle between u and the gradient vector of f. In particular, because theta varies between 0 and pi, this means that the directional derivative can be at most the magnitude of the gradient and at least minus the magnitude of the gradient. In particular, we see that the directional derivative of f in the direction u is maximized when theta equals 0, which means that the gradient vector and u point in the same direction, and is minimized, i.e. attains this minimum value, when theta is equal to pi. This is the same as saying that the gradient vector and u point in opposite directions. So what does this tell us about f? Well, in fact, this tells us that we have the greatest increase when u is pointing in the direction of the gradient vector. So this must mean that the gradient vector of f in fact points in the direction of greatest increase of f at A. Similarly, the magnitude of the gradient vector gives us a measure of how quickly f is increasing in its direction of greatest increase. Here is the graph that we've been using to define partial derivatives, and this is a level curve diagram of this graph. So here we see that for the point AB, which is this red dot right here, on the graph, on this surface, which we've presented before at this point here, the direction of greatest increase is going to be moving up towards the peak of this hill. And we see that, in fact, in that the gradient vector of the function producing this graph is going to be pointing towards the peak of this hill. Let me just remark that all of these definitions and results, in fact, extend to scalar valued functions of many variables. In particular, we may define the directional derivative for a function of n variables, a scalar valued function of n variables, and similarly the gradient vector of f will always point in the direction of greatest increase of f. Let's now think of another interpretation of the gradient that we can use by considering what it must mean for the directional derivative to be equal to 0. Well, let's suppose again that we have a two-variabled function, two-variabled scalar function, and suppose that at some point A, and for some non-zero vector v, its directional derivative is equal to 0. In particular, this must mean that the gradient vector times v has to be equal to 0. We will in fact see that if v is a vector satisfying this property, then v must be parallel to the tangent line to a level curve of f at A. And in fact, we will see much more. We will see that the gradient vector, the gradient of f, is in fact perpendicular to the level curve passing through A. Well, let's see why this should be true. Suppose that we take a level curve of f that's passing through A, and let's give that level curve a parameterization by a path r. Moreover, suppose that r of 0 equals A. Then, because the path, the image of the path, is a level curve of f, all of the outputs of r, when I plug them into f, must get mapped to some constant value. Now, if I take the derivative of both sides, well, the right-hand side here will be 0, and using the chain rule, we can compute the derivative of the composition on the left-hand side. So we recall the chain rule. This says that the derivative of composition corresponds to multiplying appropriate matrices together. And remembering that the derivative of a path is precisely the velocity vector, and the derivative of a scalar valued function is precisely the gradient vector, we must have that the gradient of f times the velocity vector of the path at 0 are in fact give a product of 0. Again, considering the gradient vector as a column vector, this is the same as saying that the gradient vector of f must be perpendicular to the tangent line of the path at t equals 0. This is the same as saying that the gradient vector of f is perpendicular to the tangent line of the level curve at A. In particular, if v is a vector that gives directional derivative being equal to 0, then this vector, must be perpendicular to the gradient vector. So in particular, it must be parallel to the tangent line of the level curve passing through A. For example, if we recall the following function from homework, then you will have already computed that the gradient vector of f at the point 0, 1 is the row vector 2, minus 1, and the tangent line to the level curve passing through 0, 1 can be computed to be the line y equals 2x plus 1. Here we see that this tangent line is certainly tangent to this level curve. This idea actually generalizes. For example, if I take a function f of 3 variables and it's differentiable and we consider a level surface S, then in fact the gradient vector of f is going to be perpendicular to S at A. This is in complete analogy with what we've said before, saying that the gradient of f was perpendicular to a level curve. In particular, in this situation, if the gradient vector is non-zero, then the gradient vector must be a normal vector to the tangent plane of S at A. This is something we've already seen when we've looked at level curves, level surfaces, which arise as graphs of functions. We've seen that the tangent plane to a graph has normal, which comes from the gradient of our function f. Here's an example for the unit sphere that allows us to compute the tangent plane at any point A.